Hello. Here's an item on number theory. Find the prime factors of 5 raised to 14 minus 30 plus 5 raised to 13. Credits to the Philippine Mathematical Olympiad for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so we want to find the prime factorization of this number. So our first instinct is to factor whatever we can factor. So we could factor out a 5 because 5 raised to 14, the 30, and 5 raised to 13, they're all multiples of 5. Now factoring the 5 is going to give me this. So the next thing we have to deal with is this thing. But it's not really obvious on how to factor that. But you could incorporate the knowledge of like factoring by grouping. So in fact, what I'm going to do here, although it's not going to be that obvious, but whenever we're given with something like this, we try to see some creative ways to factor this thing. So take a look at 5 raised to 13 and 5 raised to 12. I could see that I could factor out a 5 raised to 12 from both of them. And if I do that, I see that after factoring 5 raised to 12 from these two green terms, it's going to become 5 raised to 12 times 5 plus 1. And well, 5 plus 1, that's just 6. And that's going to give me a nice factor of a nice factor of 6 from the expression here. So I could factor out a 6, and that's going to give me this to be the factored form so far. So I could factor out a 6, and then I'll just have 5 raised to 12 minus, well, 1 is going to come from this factor. So there we go, we're going to have this. So we just continue from here. Now, the 5 raised to 12 minus 1, we can factor it via the difference of two squares. Technically, it's of this format, x squared minus y squared. So I can factor it into these two terms. And then these two terms, they both have an exponent of 6. Technically, the 1 is also 1 raised to 6. So I could use the difference and the sum of two cubes. So I can further factor them accordingly. So by the difference of two cubes and the sum of two cubes. Okay? Now, these values are a little bit smaller now, and I could easily get the value of them individually. So these values, like 1 by 1, 5 squared minus 1, that's 25 minus 1, that's 24. 5 to the 4th plus 5 squared plus 1, that's going to be 651. 5 squared plus 1 is 26. And then 5 to the 4th minus 5 squared plus 1, that's 601. And now we try to factor them one by one, okay? Now, the 6 here, that's just going to be 2 times 3. The 24, I know it's going to be 2 cubed times 3. 651, the sum of the digits is 12. So there is an obvious factor of 3. So it's 3 times 217. Now, I think this number is pretty obvious to be divisible by 7. And 217, if I divide it by 7, that's 31. So 217 is 7 times 31. All right? That's the prime factorization of that. 26 is obviously 2 times 13. And then the 601, no immediate obvious factors yet. So you guys can use the Sieve of Eratosthenes, which states that you have to just check for primes less than or equal to the square root of 601. Now, square root of 601, I'm pretty sure that's less than the square root of 625. And the square root of 625 is 25. So I could just kind of check for prime numbers less than 25. And well, if I were to list them all down, it's going to be 2, 3, 5, 7, 11, 13, 17, 19, and 23. And I'm just going to directly say that 601 is not divisible by any of these prime numbers. And if it doesn't work, like if it doesn't work for all the primes less than or equal to its square root, the Sieve of Eratosthenes tells you that 601 is going to be prime, right? So I mean, that's just one of the easier ways to determine if the number is prime, because well, we just have to check until it's square root. So that's just a way for us to kind of check whether a number is prime or composite, right? Now, if ever there is a factor that works, then obviously it's not going to be composite, so keep factoring it. But in this case, I'm just going to tell you that the 601, it's not divisible by any of the numbers here. So by the Sieve of Eratosthenes, 601 must be prime. So 601 is just going to be 601 like this. All right, now I could write this in the prime factorization, but we're only kind of interested in the prime factors anyway. So I do have a 5 here, so let me include that as well. So I have I have 1, 2, 3, 4, 5, 2, so 2 raised to 5, and then 3, 1, 2, 3, right, just 3 threes. Next, we have 5 and just 1 5. We have 1 7. We have 1 13. We have 1 31, and then we have 1 601. So, all right, the prime factors, I guess it's going to be 2, 3, 5, 7, 13, 31, and 601, a total of 7 factors. And these will be the prime factors of the given expression. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.